Hello and welcome to section 14.3. It's our second last section for the electro unit, and it's just looking at a different type of cell. This type of cell, called the electrolytic cell, it doesn't have, as you can see, it's not split up. It's only in one container, one electrolyte. And another thing is that it does not produce voltage. It actually needs voltage. It requires voltage. So I'm going to go over the differences and similarities of a voltaic cell compared to an electrolytic cell. And that's pretty much the majority of the time that we're going to spend today. So recall that in a voltaic cell, the strongest oxidizing agent, or the SOA, is always above the strongest reducing agent, or the SRA, in a redox table. Recall too that the cell potential is positive and that electrons flow spontaneously from the anode to the cathode. And one more, sorry. And that the voltaic cells are made up of two half cells, each with its own electrolyte. So they're divided, and there's also a salt bridge. You notice that there's a salt bridge. And you know that with the salt bridge, it allows for movement of ions. Movement of ions. Now let's compare that to an electrolytic cell. The strongest oxidizing agent is always below. That's an important difference. So your SOA is below your SRA, which tells us something. That tells us it's not spontaneous, right? It's a non-spontaneous reaction. So what that means is that it doesn't actually happen. And that is why if we include a power supply, then we're actually forcing the reaction to happen. The cell potential is negative, right? And it's negative because in this case here, it's the voltage needed. It's the voltage needed for the reaction to occur, whereas in a voltaic cell, it's the voltage produced. That's why it's a positive number. Electrons are pulled from the anode to the cathode via a battery or a power supply. Now, this is the same. It goes from the anode to the cathode. That's the same in voltaic cells. The only difference is in an electrolytic cell, the anode is positive and the cathode is negative, okay? And that's because we're using a power supply, and a power supply is what provides the electrons to move. And both electrodes are in the same electrolyte, and it's not divided, whereas in a voltaic cell, there's two electrolytes. And let me just go back one more. Electrolysis, just so you guys know for purposes of definition, electrolysis is the process of supplying electrical energy to force a non-spontaneous reaction. So that's why when we're finding our cell potential, it's going to be a negative value, and that's the amount of voltage that's needed in order for the reaction to occur. So now I've actually included a table from your textbook that it compares things side by side so you can actually see what's going on. So spontaneity of voltaic cell, it's spontaneous, right? Whereas an electrolytic cell is non-spontaneous. The standard cell potential is positive because it's the voltage that is made or produced. And in an electrolytic cell, it's negative because it's the voltage required. So for the cathode, let's take a look here. The strongest oxidizing agent present undergoes a reduction, and it's your positive electrode. Let's take a look at the electrolytic cell. The strongest oxidizing agent present undergoes reduction, so this is the same. However, the difference comes here. It's a negative electrode for electrolytic, and it's a positive electrode for voltaic. So let's talk about what's happening in the anode. So what's happening in the anode is your strongest reducing agent present undergoes oxidation, and that's the same, right? Strongest reducing agent present undergoes oxidation. The difference is in a voltaic cell, your anode is negative, and in an electrolytic cell, your anode is a positive electrode. So that's a difference. Let's take a look at the direction of electron movement. It goes from the anode to the cathode in both. The anode is your negative and it's your positive. That's because your electrons are produced in the anode, okay? Or at the anode. Whereas here, your anode is positive and your cathode is negative. But it still goes from anode to positive because electrons are supplied via a power supply. Direction of ion movement is exactly the same. Ions move to the anode, cations move to the cathode. That's the exact same in both. So in an electrolytic cell, the chemical reaction is the reverse of that of a spontaneous cell. During the recharging, a secondary cell is functioning as an electrolytic cell. Okay. So let's take a look in the potassium iodine electrolytic cell synthesis here. Basically, you'll take a look at all your entities. And we use here's our electrolyte. And we realize that in this case here, these are carbon electrodes, so they're not metal, right? So they're inert electrodes. We have to decide what our SRA and our SOA, and if we take a look here, there's let's take a look at what's going on. And when we find our potential, we see that it's negative. Okie dokie? Because we're comparing the SRA and the SOA, and this time the SRA is above the SOA, making it non-spontaneous. And when we find our voltage, we see that it's negative, and that's because it requires, in order for this cell to happen, 1.37 volts of power to make this spontaneous reaction actually occur. So here's another example, an electrolytic cell containing cobalt-2 chloride solution. So we have this that's going to break down into ions, and solution implies water, and electrodes. So electrodes meaning there's 2 lead electrodes, and lead is your solid. These are your electrodes, right? Is assembled, and here's our annotated version of what you have. Predict the reactions at the cathode and the anode and in the overall cell. Draw and label a cell diagram, and we're going to find the minimum voltage that must be applied in order for the non-spontaneous reaction to occur. Let's take a look and find all of our entities. Water is an entity, but it's found way low as an OA and it's found quite high as an RA. So we don't really use that, but we can find lead solid, and that's going to be our SRA because it's found at, that's the most bottom right-hand corner thing. And our SOA is your cobalt. Okay, so here we go. Here's the issue. SRA is above the SOA. That tells you it's an electrolytic cell, and it should require minimum voltage. So that's where we write our half reactions. That's our net reaction. And there is our power. This is the drawing of it. The electrodes are the same. Okay. The electrons are still moving from the anode, right? So the electrons are moving from the anode to the cathode, but make sure that you include the fact that your anode is positive, your cathode is negative. And your anions are still traveling towards the anode, and your cations are still traveling toward the cathode. You need to include the fact that there's a power supply. So in order to find the minimum voltage, we just use our cathode subtract our anode, and we get a negative number. Okay, and that just tells you that we require 0.15 volts of power a minimum of in order for that cell to work. So here's another question. An electrolytic cell set up with a power supply connected to 2 nickel electrodes. So we have 2 nickel electrodes. Immersed in an aqueous solution containing cadmium nitrate and zinc nitrate. Cool. Predict the equations for the initial reaction at each electrode and the net cell reaction. Calculate the minimum voltage that must be applied. So these are the types of questions you're going to get, and they're pretty repetitive. So here, much shorter version, we have our SRA. You identify your SRA, your SOA. You write out your the reaction that's happening at the cathode, the reaction that's happening, the half reaction that's happening at the anode. Make sure this time you can include your voltages. There's your net reaction, and here is your answer for the voltage that is required in order for that cell to actually work. It requires 0.14 voltage of 0.14. So evaluation of predicted reactions, the chloride anomaly. The chloride anomaly happens if 2 things are in place. It's an electrolytic cell, and the second one is that it only occurs between chlorine or chloride and water. So the data table indicates that water is your stronger reducing agent than the chloride ions. Okay, if we take a look and find, here's our chloride ions, and here we have our water. Let's see here. Water is a stronger reducing agent than our chloride ions. And here's our water. However, the chloride anomaly states, right, that for the electrolysis of solutions containing the chloride ion, and an example of a chloride ion solution would be brine, the chloride ion acts as the strongest reducing agent. So only when you're comparing, when you have 2 things left and you have to compare water to chloride ions, the chloride ion is going to trump the water, even though it doesn't show that with your table. Okay, this is one of those exceptions. And like I said, it only works when you're comparing chloride ions and water. That's it. Science and technology of electrolysis, production of elements. Most elements occur naturally combined with other elements and compounds. The production of active metals, strong reducing agents, from their minerals typically involves electrolysis of molten compounds of the metal. So here's an example. Many active metals are weaker oxidizing agents than water. So if aqueous solutions are electrolyzed, water will be reduced instead of the solid metal you want to produce. So what we do is we take a look at the molten salt electrolysis. Metal cations move to the cathode and are reduced to metals, and nonmetal anions move to the anode and are oxidized to nonmetals. So it's just telling you what happens with molten using electrolysis and molten entities. Here's an example. Lithium is the least dense of all metals and is a very strong reducing agent. Both qualities make it an excellent anode for batteries. Lithium can be produced by electrolysis of molten lithium chloride at a temperature greater than 605 degrees Celsius, the melting point of lithium chloride. And write the equations for the cathode and anode half reactions and the net reaction. So that's what's happening at the cathode, what's happening at the anode, and there's our net reaction. So now what I'm going to do is just go over some definitions and some examples of what happens with electrolysis. Now, you're not going to be tested on this, but it would be part of like an info box. So the electrolysis of aluminum ore is problematic because of the high melting point of your aluminum oxide. Aluminum oxide dissolves in a molten mineral called cryolite, which acts as an inert solvent for the electrolysis of aluminum oxide. So just an example, in order to create aluminum, this is what has to happen. And there's your overall reaction with aluminum being produced from its ore. And like I said, definitely don't have to memorize this. You just have to understand the fact that things have to be molten in order for the metals to be produced. The most important nonmetal produced by electrolysis is chlorine. The chloralkali process is the electrolysis of brine. So this will break down into its ions, right? It's going to break down into the sodium. and chloride ions to produce chlorine, hydrogen, and sodium hydroxide. Remember, the chloride ions act as the reducing agent instead of water, and this is another example of the chloride anomaly. And remember, it's only when you're comparing chloride ions and water. And here we have the production of chlorine gas. This is an example of electrolytic cells. Refining of metals. Electrorefining is the process of using an electrolytic cell to obtain high-grade metals at the cathode from an impure metal at the anode. So that's kind of cool that you're actually producing metals and they're becoming pure. It's pure metal. Electrowinning is a process of using an electrolytic cell to reduce metal cations from a molten or aqueous electrolyte at the cathode. So that's kind of cool. And like I said, this kind of information will be used as an info box. It is not something you have to memorize. Electroplating is a deposition of a metallic coating into an object by putting a negative charge into the object and immersing it into a solution, which contains a salt of the metal to be deposited. The metallic ions of the salt carry a positive charge and are attracted to the object. And when they reach it, the negatively charged object provides the electrons to reduce the positively charged ions to the metallic form. So here, in this case here, the spoon is being electroplated, okay, with silver. So that's kind of cool. And that's it, kiddos. That's all we have for this particular section. Make sure you know the difference between electrolytic cells and voltaic cells, and make sure you're able to compare and contrast them. Okay, have a great day.